So our next talk is going to be by Anna Wuest. She is at the Dana-Farber Cancer Institute and the Harvard T.H. Chan Public Health School of Public Health. And she is going to be talking to us about another application of flour in the health direction. The title of her talk is Demonstrating a Federated Learning Workflow for Pancreatic Segmentation Model. So over to you, Anna.
Okay, hi, thank you so much for having me. I'm very excited to present today. So yes, so I'm Anna. I did this project in conjunction with Junie Guo and our advisor, Alex Chattery. Unfortunately, I don't think they're here today, but I'm still excited to share what we learned with you. So for a little bit of context, Junie and I completed this project as our capstone course at Harvard School of Public Health, and we did this in conjunction with Dana-Farber, which is where I now work, and with Flower, of course. So what you should expect from this presentation is really just a very granular example of how flour might be used in a healthcare setting. And in this case, we're using a unit segmentation model to segment the pancreas. So you can definitely expect some background details in healthcare, as well as some brief overviews of model construction, how we use flour in this case, and our results, which I'm very excited about. So background, as I'm sure many of you may know, healthcare data is very expensive to collect and very hard to share due to privacy concerns. And of course, in the last presentation, Micah touched on a lot of these topics. So to circumvent this, federated learning has been proposed to train models in this decentralized manner to expand use of healthcare data in these models. But it is important to note that there is a very large variation in hospitals' data science capabilities. And of course, federated learning is not really widely used in healthcare in this moment. And I just want to touch on that because while Dana-Farber does have a very robust data science department, this is not, of course, true for every hospital that might use federated learning. So that's just a good thing to keep in your head with this process. So I'll talk a little bit about healthcare data, and in this case, the pancreas. So the pancreas is a small organ located in the abdomen. It's really important for regulating the digestive tract and blood sugar through enzymes. However, it is prone to both cancerous and non-cancerous nodes. And this is particularly concerning because the pancreas, when the pancreas has a cancerous node, this is not kind of easily displayed through symptoms until very late stages. So it's very difficult to identify and treat pancreas cancer. In addition to this, for any kind of model that might segment and look at the abdomen, the pancreas in particular is very difficult to segment properly because it moves around a lot, and any kind of segmentation data is long and difficult to have because it takes a lot of trained eyes and time to kind of go through and identify what the pancreas is. And we can really see that in these images. So in the first one, to me, I'm not an expert in CT scans at all. And to me, it just kind of looks like one dot of an organ amongst many dots of an organ. I would have no indication that this is a pancreas. And here is another image where the pancreas shape is a bit more evident. But again, at the end of the pancreas segmentation, it's kind of looks like it's almost in a different location and is not really the shape we would intuitively think of with the pancreas. So of course, to the untrained eye, segmentation is not really possible, but even for segmentation experts who we worked with in this case, segmentation can take a very long time to conduct, especially with the amount of images that we might need for this process. So here are the three kind of sample data sets that we were using in this case. Unfortunately, Junie and I were still students at the time, and we did not have access to any real world data. So we kind of had to make do with what we have, which were these open source data sets. And you can see that there is quite a bit of variation between these data sets. So the smallest is the SNAPS data sets, or the multi-atlas labeling challenge. And this has 30 patients with over 3,000 scans. This is overall a small data set for this use, but I'm sure you can imagine how long it might take to segment a large data set. And And in this case, our largest data set is the medical segmentation decathlon, or TASC-07, with almost 300 patients and over 26,000 total scans. So data collection in terms of any kind of augment segmentation can be really tough because of the necessity of these specific segmentations. Another concern is the average target. So this is the percent that the pancreas was actually identified in each segmentation scan. In each case, it was less than 1%. So there really is a big concern with how much data has the pancreas and does not have the pancreas for this model. And then one last note, this is not displayed in this, but even the CT scans are very different. So they're used on different machines, which might model how different hospitals could vary with their machines. And this could include something like the distance between scans differ. So also an important note for model training. So again, as Micah had mentioned before, the pre-processing steps just took the longest in this case. We only did this over the course of one semester, and we probably spent about 3/4 of the time just looking at the pre-processing. This is largely because the data sets, while clean within themselves, did not make sense with each other. So we had to do a lot of rotation, windowing, label unification before we could finally construct the 2.5D segmentation that we needed for the UNet model. And this was really for setup. So we have one center image and then of course the 2 contextual images for each prediction. So here, just to really drive the point home with how different these data sets were while consistent within themselves, you can see at the top part, they are kind of turned different ways. You have kind of different noise on the outside. And not pictured here is even the scan orientation is different. So some are top down and others are bottom up. At the bottom, you see what the scans look like after the respective transformations. Here we can kind of see the UNet model, which we used, including the data of how it's put in. So we have the 3 scans, 1 main and 2 contextual, and then the output scan with a VGG16 pre-trained encoder. And the UNet model is the typical model used in organ segmentation. So finally, to deal with the data issues I mentioned previously, we use the DICE score to kind of weight the evaluation, or the DICE score for a more weighted evaluation metric, so that we can prioritize the correct labeling of the pancreas as opposed to the correct labeling of the non-pancreas. And then of course, we use a binary cross entropy loss with tuning of the positive weights to make up for the data imbalance. So as many of you know, I'm sure you're very familiar with flowers. So I will just run through this example very quickly. But in our case, we just set up a client for each data set. So TCIA, Synapse data, and the TASC-07 data with our server. And we did this all through GCP. And of course, as you're all familiar with, we use this to train and receive the weights back. And the same was true with the evaluation, the aggregated evaluation metrics. And then we go to our results, which in my opinion are very compelling and we were very excited about. So just to kind of take some time to walk you through this and maybe some examples of what this could mean. So on the left, you can see each of the 4 types of models. So we have the first 3 of a model just trained on one data set and the model trained with federated learning. And on the top, we see each individual data set. And then here we see the performances that each model had on each respective data set. So starting if we look diagonally of the models that were trained on the data set and how they performed on their own data set, we kind of see a few different stories. So starting with TCIA, this performed pretty well. Close to 70% is not too bad for organ segmentation. However, Synapse is really performed quite poorly. It only has about a 34% accuracy rate, which is not usable at all. However, TASC-07 performs really well. And if you remember the sizes of the data, for example, this might be pretty expected. So TASC-07 had over 26,000 individual scans, while Synapse had only a little less than 4,000. So this disparity probably explains quite a bit of the disparity between the actual performances. And TCIA was kind of in the middle with 80 patients, but definitely was closer to the size of Synapse and TASC-07. If we look at each individual row, we can see, again, 3 different stories of generalizability. So for TASC-07, which performed very well, this did generally perform well with each of the other data sets as well, are all surpassing or close to about 70%, which indicates that this size and the qualities of this data set probably did generalize very well. However, with Synapse, this did poorly with the other ones, as it did poorly with itself, which of course is expected with such a small data set. And then TCI is particularly interesting because it performed well with itself, but not with the other data sets, suggesting really poor generalizability and a model that if used in one hospital, if each of these data sets kind of represented its own hospital, would work well enough on its own, but would not work well on other hospitals that might have different demographics. And this is really a significant cause for concern in the healthcare industry. We don't want to deploy models that don't generalize well, especially to hospitals that have different demographic data, which finally leads us to the federated learning, which I find really incredible and really compelling if you're not already on the Flower train already. You can see the best performance overall is now with Synapse, which didn't even perform well with itself initially, and now we're at over 80%. For TCI, again, the best performance for TCI was a federated learning model, and finally TASCA7, while not surpassing itself, performed quite well overall. So this suggests good generalizability. This suggests a way to kind of perhaps allow hospitals that don't have enough data for even themselves to be included in models that are very generalizable and can be used in other hospitals and functions. And overall, I just find this to be very important results. So again, we can kind of see comparisons of what these segmentations actually look like. So these are two separate scans. We see the ground truth here of what the radiologist labeled. We see the federated learning prediction, which seems to match up pretty closely in both cases. Then we see TCI and Synapse, which again, in both cases, don't match up well at all. The TCI at least suggests where the pancreas is located, but overall not great segmentation. And then finally TASCA7, which similar to the federated learning performs decently well. So the big takeaways are that federated learning shows marked improvements for this very granular study and can really help with generalizability as well as adjusting for small data sets, which is probably very common in smaller hospitals or hospitals that don't have time to spend as much time with like research and segmenting all this data. And I think this really shows a lot of promise for increasing access for advanced model for community hospitals, as well as working together to just improve the models and improve their demographic scope overall. So some future directions we were thinking about, but we haven't quite done yet, is just the utilization of ML-cubes and MedPerf to continue this benchmarking process and standardization process, as well as using TASCA7 to segment for actual tumors in the pancreas. So those are, that was my presentation, and a special thank you to everyone I worked with. I had no idea anything about federated learning prior to this, and it was so easy to use Flower. Most of the time was really just the data preprocessing. So I found this really exciting, and I'm glad to be able to share with all you. So thank you again, and here's my email in case there's any questions I'm not able to answer now.
Thank you, Anna. That was a great talk.